So, all right. So we'll just resume from there. So nothing to be to be worried about this equation. It's very straightforward. I'll just do a small derivation. You all know del G is del Z0 plus RT ln K, right? This is the equation we've long been using. So if you just divide it by NF, everything by NF, this is also by NF. So this becomes your minus E, this becomes your minus E0. So if you just take the minus inside, it will be negative, so it becomes RT by NF. This is very simple reaction. But K and Q all the same. There is the equilibrium constants, and that is the activity of the product species divided by the activities of the reactant species. Okay, so here we will see what is happening. So first let me tell you what are the half cells, right? I just talked about half cells. One is being oxidized, the other is being reduced. So let's see what is being done here. It's a combined equation for the whole cell. So alumina, let's take example of the carbon. It's easier to track carbon. Carbon from zero state, the final state is CO2, right? So oxygen we know always -4, so that's +4. So what is being done here is carbon, right? Has 4 electron. It's giving up 4 electron to produce CO2. So we normally don't write it in this way. Carbon plus half plus O2. So that's CO2. This 4 electrons which carbon has given up will be taken up by aluminium. So aluminium, for aluminium it is 2/3 Al2, or let's say just for balancing it has been written like this, 4 electron plus, so Al2 3, if you just see -6 here, so it has to be +3 state, so net difference is -3 plus 2 6, it's balanced. So here the aluminium 3 plus ion, so here the aluminium 3 plus ion will take this 4 electron to form aluminium. Now to balance this 4 electron, I have to do it in a way so that the 4 electron gets balanced. So if I take 4 here, so 1, so if I do Al2O3 and 2/3, we will put it 3, so it's basically taking out the 4 electrons, right? 2 to 4, right? And this +3 is being managed by this one. So basically 2 to 4, 3, 12. So 2 to 4 and +3, so +12 by 3. So net 4 positive charge needs to be balanced. So that is balanced by here. So it becomes 4/3 aluminium. You understand this way, right? This is very important, 4 electron. Why? You remember we are talking about NFE0. Del G0 is equal to minus NFE0. This N you have to compute from the equation. That is the net transfer of electrons. So always remember the transfer of electrons are constant. That is the exact number of electrons given up by the reducing species, or this is being see carbon is being oxidized, right? 0 to +4. So it's a reducing species here, and oxygen, aluminium is being reduced, +3 state to 0, +3 state to 0, right? So it's a reducing it's being itself reduced, so it's an oxidizing species. So this cell is carbon -4e. So this cell, oxidation is being done. So this is oxidation, right? So this is anode. Electrons are there. Left anode negative, right? So electrons are there. So oxidation. This is the oxidation part. Carbon from 0 goes to +4. And this is the reduction part. This is the reduction part. So if I just write it clearly for your visualization, I'll just write it clearly. So left anode oxidation, right? We write for this. Yes. Left anode oxidation, also say negative, right? For this reaction, it is the half cell. So see, we have oxidation. We will talk about aluminium. So aluminium 2/3 Al2 plus 4 electrons, because this is +3. Again 2 to 4, 3, 12. 12 by 3. So net 4 electrons transferred. Right? 2 to 4, 3, 12 divided by 3, nets 4 electron transferred to have my 4/3 aluminium, the 0 state. Right? This 4 electron it got from the cathodic reaction. Cathode. With the cathode, I have, this is the right of the cell, we call it. The cathode reaction is the right reaction. By convention, the cathode reaction we say is the right half cell. It's the left half of the cell. It's by convention. Whereas the cathode reaction is taking place, it's the right half of the cell. So for the cathodic reaction, it's also positive. Actually, the electrons is being taken up here, right? It's producing. Sorry, cathode reaction is it's negative. It's positive actually. I have made a mistake. I'm sorry, I've made a mistake. I'm talking about oxidation, right? Sometimes I also make a mistake. Oxidation, I just made a mistake. Sorry. Carbon plus 4 electron gives rise to CO2 plus O2 gives rise to CO2 plus 4 minus 4. So it's leaving the 4 electrons. The oxidation is taking place here. Carbon from 0 state goes to 4 state, plus 4. So 0 to plus 4, this is the oxidation. Increase in the valency number. So this is the oxidation reaction. Okay, so electrons are being produced at anode, which is by convention is the left half cell of the electrochemical cell. This is the left half of the electrochemical cell. This is the anode. This is the oxidation is taking place. For the cathode, the other half, cathode right half, or here we call it a positive, but these 4 electrons will be taken up by aluminium here. Aluminium 2/3 aluminium plus 3 into 2 to 4, 3, 12, 4 electrons. So I will rather say so minus 4 electrons, right? This is leaving my 4 electrons. So it's taking 4 electrons. Now it's everything is in shape, right? Gives rise to 4/3 aluminium 0. So this is the main reaction. Aluminium is being reduced plus 3 to 0. This is a reduction reaction. It's also the right half of the cell. Carbon is being oxidized. So it's being so this is a reducing agent, carbon. So carbon is the reducing agent here. It gets itself oxidized and it reduces aluminium. Right? So this is the concept of any electrochemical cell. So you don't need to do these steps, but you need to understand what you are doing. The most essential step in finding this out, the number of electrons. People don't understand how many electrons has been transferred. Always go for an element which is existing in a less complicated with its stoichiometric coefficient. For example, carbon goes to CO2. So there is definitely 0 to plus 4. But if you need to calculate it to aluminium, there will be a bit difficulty. It's possible, absolutely okay with this. So 2/3 automatically comes from here. This 2/3 has to be value, so plus 3 by 2. So automatically if you do this, 2 to 3, 2 to 4, 3, 12 by 3, so 4 electrons are required. But if I look at carbon, it's easier for me to visualize the number of electrons transferred, right? So the first thing you should approach a problem of electrochemistry, find the number of electrons transferred in the process. Okay, so the next step here, so I know the number of electrons is 4. So once you know that, the rest step is very easy, very easy. The rest step is del Z0 is minus NF E0. You need to calculate E0. So E0 is nothing but del G0 by NF. So my del G at that temperature is 452 kilojoule, or let's say put it in kilojoule, divided by 4 is a negative sign, okay? Always remember this. 452, also put it, okay, I will just put it. 452 kilojoule is equal to 452 10 to the power 3 joules divided by N, which is 4, and 96,500 is the Faraday's constant. So if you do the division, you will get a value like how much? I'm sorry, what's the value? Yes, it will come to about minus 1.17 volts. So minus 1.17 volts is your answer, right? That's how you solve the free energy change for an electrochemical reaction. It appeared in GATE 2007. So let's now move on to the second part of the question. When the activity of alumina is 0.1, the EMF of the cell is. Now you have been now asked the alumina, nothing is given, right? Here, if everything is existing in standard state, I'll just write the equation. Now the second part of the equation needs to be used. That equation is useful now. So if we just write for any state, not for the standard state, what will be my E? What will be my E for any arbitrary state? It will be E0 minus RT by NF. For this particular reaction, how it will look like? For this reaction, please note it down. It will be like this. Activity not of alumina. See, whenever we are writing equations, please remember that here we are talking about ions. Okay. So if you just look at the ions, so it will be like something like 2/3 Al2. So it will be 3 plus. You can do that, but let's do it in or we can always do that into 3 plus. You can just put into this way, or you can just write the activity itself. So you can always write in as the activity of aluminium. You know the stoichiometry is 4/3, so it will be raised to 4/3. Carbon dioxide, it's a gas, so PCO2 stoichiometry is 1 divided by activity of alumina raised to the power 2/3 and activity of carbon. Right? This is the equation. This is the equation for any state. Once you were asked that find the EMF of the cell when alumina is not existing in standard form, whereas its activity is 0.1. Its activity is 0.1. So for these reactions, I need to substitute. What about the others? If nothing is given, always remember PCO2 is equal to 1 atmospheric pressure. If nothing is given, it's existing in this solid form, it's in pure form, so this activity is 1. Nothing is mentioned about aluminium, so pure aluminium is deposited, so activity is 1. So only thing we are left up with this alumina concentration or the alumina or the activity of alumina. So if I just do it, so it will be minus 1.17, which I have calculated from the first part, the standard EMF of the cell, minus 8.314 multiplied by the same temperature, 1273, I guess, 1273 divided by 4 electrons, as it's same, 96,500, logarithm of 0.1 to the power minus 2 by 3. So it occurs at the denominator. So logarithm of minus 2 by 3. 0.1 is the activity, 2/3. So 1 by 0.1 to the power 2/3 is same as 0.1 to the power minus 2 by 3. Right? If you substitute this equation, you will get minus 1.21 volts. Is the answer. Right? Okay. Let's move on. Let's solve another problem. Let's solve another problem. Let's solve the problem. Just pause the video, note some values down. So I'll solve two conceptual problems. Before that, you just note this down. It's not exactly 2014. The second has appeared, I guess, in the 2012, and it's all between 2010 to 2014. I exactly don't remember the years. I just sorting out these questions. So you just check it out. It's all after 2010 to 2014 problems. Right. So I think so. You have noted down. So I will solve another problem. It's pretty straightforward problem. It's also based on aluminum reduction. 6E is raised to 3H2 plus An. I am solving the question number 33. Delta G0 is given as 897.3 kilojoule. Right? But the hydrogen concentration ion is unity. The reduction potential H plus concentration is given to be 1. And reduction potential of the reaction under standard state will be fine. So let's come back to the original video. So again, it's very straightforward. Nothing is being, everything has been given. The electrons also been given. So nothing else. You just do del 0 is equal to minus NFE0. So UE0 becomes 897.3 into 10 to the power 3 divided by 6 electrons in this process. So N is 6 multiplied by 96500 with a negative sign. That will give you a result of minus 1.55 volts. It's a very straightforward problem answer. Right? Minus 1.55 volts. Minus 1.55 volts. This is your answer. So it was again a very straightforward. So this equation is very important. E is equal to E0 minus RT by NF log K. Okay. Nonce equation. Fine. Let's now go to a very conceptual problem now. This is the conceptual problem that I have found it, and it's very interesting. Read the question 40 very carefully. I'll just explain this question. This is not a straightforward question. This kind of questions require something you need to understand certain things. Okay. I'll read it for you. I'll just explain a bit for you in this question. For the following electrochemical reaction, Sn plus 2H plus Sn2 plus H2, if the solution has Sn2 plus concentration of 10 to the power minus 2 moles and pH 5 at 298 K, which of the following is true? Given standard reduction potential of Sn2 plus 2 minus is Sn is 0.136 volt. See, first thing is that you need to break it up into two parts. Let's solve this problem. You will understand. as I go along this problem. Let's solve this problem.